Hello and welcome to Engineering Problem and Solution. And today we are going to look at the topic three-phase circuit analysis under the balance load condition. So I have a example one here, and let's look at this example one. So there is a three inductor coil having per phase resistance of 40 ohms. So we have 40 ohm resistor and inductive reactance of 30 ohm are connected in star across 415 volt, three phase 50 hertz supply. And what we need to analyze the circuit by finding the rating of three capacitors. So we need to find the capacitor value, which must be connected in a star to the load in order to bring the overall power factor of the circuit to unity. And this unity means is a 1. So we need to bring power factor back to 1. So first thing we need to find out is what is the value of present circuit power factor, and we need to bring that present power factor of the circuit to back to 1. Now before we start solving or analyzing this problem, to make things easy, let's construct the circuit diagram for this example. So the based on this, you can clearly see that is a three phase circuit, and three-phase circuit has balanced load. And balanced load, let's draw the three-phase. And what type of three-phase circuit we have to draw? Is a star, you can see here is a star connection. So let's draw the star connection. So we have a resistor and inductor, and then we have resistor and inductor, and then we have resistor and inductor in three phase. Okay, so this is our three phase, and this is our load side, or we can say load, and then we have a supply on our this side. So we don't need to draw our supply, but we know the voltage across our line to line voltage is VL, which is our 415 volt, and line to line voltage, which is here also, is VL is 415 volt. And the value of resistor is 40 ohms, which is R, which is L is the value of L is not given to us, but value of inductive reactance is given to us. So that is going to be XL. So the value of XL is given to us is 30 ohm. And since it's a balanced load, we have same value of R and XL, R and XL, which is 40 ohms and 30 ohms. 40 ohms and 30 ohms. Okay, all right. So this is our circuit for three phase, based on our example one. Okay, now what we are going to do is, what we're going to do is, let's analyze this furthermore. So since the circuit is balanced, from this circuit we can say from this circuit we can see that it's a balanced load. Balanced load means you have same value of resistor, inductor, or same value of impedance. I will say same value of impedance. So this is called impedance in a one phase. Okay, single phase. There is three single phase. So in one phase you have same value, on other phase as well. There is a same value. So this is called balanced load. Since it is a same in all other phase, so and it is a balanced load, so we only need to analyze single phase. So we can only analyze single phase, and later on we can times with 3, and then we get our desired capacitor or current or voltage, so whatever we are calculating. So to analyze single phase of the circuit will be enough, single phase of the circuit. So let's draw a single phase of this three phase supply. So we have we'll take uh, our source, and then we have a single phase which is resistor and inductance, which is reactive inductance, and then XL, and then R. The value of R is 40 ohm, and this is 20 ohm. And what we need to do is we need to find the value of this capacitor which is connected here to improve our power factor. To improve the power factor, this is what we need to find. So what is the value of capacitor which is going to improve the power factor of this circuit? That's what we need to do. Now, to do that, the first thing we can do is to find the impedance of the circuit. So let's find the impedance of the circuit. So let find impedance. So impedance per phase, okay, which we're gonna say is ZP. So ZP is simply, you can see here, is our relationship of, if you have ever done any impedance of series, then it is can be written as simply R plus J XL minus XC. So your XC is not there, so you have just simply XL. So you can write ZP equals to R plus J XL. Okay, so we have ZP equals to 40 plus J 30, and this is your ohms. Now, since you are doing the calculation in a complex number, and this kind of format is called is your rectangular format. Now, since in electrical and electronics analysis, the rectangular format is not going to be effective, so we need to convert this rectangular. So this format is called rectangular format of the complex number. We need to convert this into polar format. So ZP. Now, how to convert this into polar format? You can do in your own way, mathematical way, or you can use calculator. So best way to do is use calculator. For that, make sure that you go into the complex mode. So for that, go to the calculator, press mode, and find complex. Once you find you are in the complex mode, then simply put that value which is given to you. So the value we have is 40, so which is our 40 plus, then you need to have 30. All right, if you look here, J is first, but in calculator the J should be after the number, so you have to put 30 then J. Since in a calculator there is no meaning of J, there is I, because it's a complex number, so you have to put I. So if you look here, this is your I which you're looking at, so there is 2I. Right, once you have this, do the equal to, and then you are going to see your answer is 40 plus yeah, that's the answer which you can see here, but we don't want that answer, we want into polar form. So how to get the answer in polar form? For that, you have to press shift and then go to the complex, which is number 2. If you do that, you need to convert into, you can see here it says display the result into polar form. You have to click that, and then you can see your answer in polar form, which is 50 angle 36.86. So that's what we're going to take. So we have 50 angle 36.86 degree ohm. Okay, this is in a polar form, and this is what we are going to use all the time in our calculation. Okay, right. So Then what we're going to do is, let me use different color. Then we are going to basically find other parameters like impedance, not impedance, basically like voltage and the current. So let's find the phase voltage. Okay, now from the question we know that the line voltage, so line voltage, I will say VL, I'm going to write here as line voltage. So the line voltage is given as 415 volt, isn't it? Let me check. So line voltage is, yeah, 415 volt. But since is a star connection, so there is one character of the star connection. So I will write here, in star connection, okay, your line current, which is, I'm going to say here IL, is equals to phase current, which is IP, and your phase voltage, okay, or let's write in terms of line. Okay, so your line voltage, which is going to be VL, is going to be root 3 times VP, which is your phase voltage. Okay, phase voltage, which is VP. So this is your relationship, don't forget that. Right, let me use red color. So your relationship is this: line voltage is root 3 times phase voltage, and line current is equal to phase current in a star. Where this happens, it happens in a star, connection. Don't forget that. Okay, so that means we can find the phase voltage then. So the phase voltage, which is VP, is going to be VL divided by root 3. So let's find that, which is our 415 divided by root 3. If we use this in a calculator, what we're going to get? We're going to get 239.6 something. So I'm going to just use 6 volt. So that's my phase voltage. And then what about the line current then? Now let's find the line current, or phase current is going to be same. So let's use our Ohm's law, very popular law in the electrical and electronics. So Ohm's law says I equals to V over R, but in AC it's going to be Z. So IP, which is our phase current, must be equals to VP divided by ZP. Now if you ask me why we use PP not LL, the reason we use PP or phase space, because we have the information about impedance. Okay, we don't have the information about line impedance. Since we have the information about phase impedance, we use VP, IP, and that's the reason we need to always calculate phase current and phase voltage all first, because we always has the information about phase impedance. And then we have VP as 239.6 divided by ZP. ZP is 50 angle. We have 50 angle 36.86 degree. Okay, so if we now, how to calculate this? Same thing. You go to the calculator in complex mode and get your answer. So we have 239. So let's go to the fraction. Okay, we have fraction 239.60, and then angle 50. Now we need to find the angle in a, if you look here, this is our angle here. So simply pressing that is not going to give us angle, so we have to press shift and then angle 50. Oh, come on. We have 50, shift, angle 36.86. So you can see still we are going to get in a rectangular format. We don't want result in rectangular format. We want in a polar formula. So this is our answer for polar format. You can see here 4.76792. Let's write that. So we got 4.792 angle minus 36.86 degree, and that's your ampere. So that's the current which we have just calculated. So we have voltage, we have current. Now what do we want? Now we want, because remember our focus or analysis is on about power factor to improve. So the power factor, now what is power factor then? So now power factor is nothing but cos theta. What is that theta stand for? The theta is angle between the current, phase current, and you can just say current, yeah, the current and voltage. So that is the angle between current and voltage. And since you have no other angle right now, the angle is, you can just see, is this value, and that's your angle which you're looking at. Okay, so power factor here is going to be cos angle of minus 36.86 degree, and that's the angle between your voltage and the current. So if you draw the phasor diagram between the voltage and current, you are going to see something like this with the lagging, because it's a negative. You're going to see lagging of 36.86 degree of I or IP or VP. And it makes sense because your inductor always lags. Okay, since there is inductor in the circuit or in the load, the current must lag by certain angle, and you can see is lagging by minus 36.86 degree. So what is our power factor in this circuit then? The value of power factor, okay, if we use calculator here, so our cos minus 36.86, we got 0.8. So the power factor we got here is 0.8. Okay, all right, let's make this. So the present power factor which we can see is 0.8, but we want that power factor to reduce or to improve to 1. Okay, so what we want, let's write that. So we want to improve the power factor present power factor, which is basically 0.8 to power factor of 1. So that means what's the angle we are focusing here? The angle we are focusing here is going to be cos inverse 1, which is theta equals to 0 degree. So we want to make the angle 0 degree. Okay, you can also highlight that. So we want to make the angle to 0 degree, and that's what we want to do. Okay, that's what our focus is. Right, to do that, what we need further more information now. We need active power and reactive power consumed by this load. So what we're going to do now, we are going to find the active power and reactive power. So active power consumed by this load, and the formula to calculate the active power, I'm going to write P here, and the formula to calculate the active power is going to be √3 times VL times IL times cos phi. There is another formula as well, which is 3 times VP IP cos phi. You can use that formula as well, okay? But if you have VL and IL, then you have to use root 3. If you're planning to use VP and IP, then you have to times with 3, and that's the formula. I'm not going to write that formula. Okay, yeah, doesn't matter. Okay, I will write it here. Or 3 times VP IP cos phi is the same. Okay, you're going to get the same answer no matter which formula you use. So let's use this formula here. So root 3, and the value of line voltage is 415 times our line current, which is a phase current, which is, now when you're using this, you don't need to take the angle, just the magnitude of current. The magnitude of the current is 4.792, okay, because you're using the angle with cos. So your 4.792 is the magnitude. Just take the magnitude of the current times power factor, whatever power factor you have calculated, or let's use minus 36.86 degree. So if we use this in a calculator, let's see what we are going to get. Let's go to the math, and then root 3 times times 415 times 4.792 times cos, which is 0.8. So we got 2755.59. 2755.95. And what's the unit of active power? The unit of active power is watts. Okay. Now we need to find the reactive power as well. Reactive power, we prefer to write reactive power as Q, and the formula is exactly same, but in place of power factor we use sine angle. So root 3 times VL times IL times sine phi. So Q equals to root 3 times 415 times 4.792. Remember, only magnitude, no angle. And then I'm using sine minus 36.86 degree. Q equals to minus, if you use this in calculator, what you're going to get? You're going to get 2066.22. The unit of reactive power is var. Okay. All right, so we got active power, we got reactive power, and it says negative reactive power. Now negative, whenever reactive power says negative, that means it's consuming the reactive power. Okay, it's consuming the reactive power, is consuming the reactive power. Right, once we have got those information, what we can do is we can draw the triangle here, just to show you basically what's happening here. Okay, so this here is, we can say, is active power, and the reactive power, since is a negative, we can draw somewhere down like that. So is a negative power here, and the sum, the addition of this active power and reactive power is going to be your apparent power. So this is going to be apparent power, and the angle which you see, which you have looked at, which is 36.86, is this angle here. This is your apparent power, and this is the value which you have just calculated now, which is 2066.22. It's negative, that's why I have drawn down, and this value here is simply how much we have calculated, 2755.95 watts. bar. Okay, so what we need to do now, we need to get rid of this angle and make this angle to 0. Okay, we need to make this angle 0. That means we need to basically make the power as same of apparent power. Okay, that is, or also that means we need something, which is going to supply this reactive power, the negative. Okay, if this is negative, then we need something positive value of that, which is going to provide same reactive power. Because if you look this triangle here, if you look this triangle here, all this reactive power is what is making the angle. So the angle is made by this reactive power. So if we can support this reactive power by something else, that means we can reduce this angle to 0 degree. Okay, so we need to provide, we need to have something there which is going to provide this reactive power to the inductor, okay, which is going to be capacitor. So what we're going to do now? So in easy term, basically in easy term, whatever reactive power we have calculated should be connected in a parallel here with the capacitor. If you look this circuit here, it should be connected in parallel with capacitor. And that capacitor is going to generate the reactive power, which is going to consume by this inductor. So this is what is going to happen. So the capacitor, which is, I'm going to say the capacitor is going to produce a current, which is IC. And that IC current is going to feed back to this XL. And that's how the reactive power will be consumed by inductor, which is produced by capacitor. Okay, and that's going to happen here. So that means what we can do to make this complicated question as normal, we have to say that let's draw the circuit. So that means let's use white color. So we need basically capacitor in a parallel, which is going to follow the IC here. This is capacitor C, this is L, this is R. So the reactive power consumed by this L is going to be produced by C. Okay, and it's going to consume by this. So that means whatever we have calculated just now, the reactive power, which is this value, which is going to generate by capacitor. So to find the IC current, in the circuit, reactive power Q of 2066.22 var must be generated by capacitor. Okay, because again, if you look the triangle here, the angle can be reduced if we can reduce this reactive power. To reduce this reactive power, we need to provide a positive value of reactive power. And who is going to produce that? Capacitor. How is going to produce that? By using current. And how to find that current? Using same value which we have calculated, which is our reactive power, using the same relationship. So that means Q equals to root 3 VLIC. Okay, and that's what we are going to find. Our relationship here is the IC. So we know all of that. We know Q is nothing but 2066.22 equals to root 3 times VL is 115, and we need IC. If we rearrange this, we're going to get IC equals to 2066.22 divided by root 3 times 415. And then if we use this in calculator, IC we are going to get is 2.87 ampere. Okay, so once we get the IC, then how to find the XL, or how to find the capacitor? Then we know that XC or IC is going to be nothing but VP divided by IC, right? So XC is going to be VP divided by IC. Same relationship of Ohm's law. Okay, same. And then we have VP is nothing but 239.60 divided by 2.87, and we got the value of XC as 83.35 ohms. Now still we haven't got our capacitor value. We got the impedance value, not the impedance value, reactance value. So we got the reactance value. How to find the capacitor value? We know the relationship. We know that XC equals to 1 over 2 pi FC, isn't it? So we have 83.35 equals to 1 over 2 pi times 50 times C. If we rearrange this, we got C equals to 1 over 2 pi times 50 times 83.35. So if we use this in a calculator, we are going to get our capacitor value C equals to 38.189 microfarad. Okay, and that's the value of capacitor which we must connect. So to reduce our power factor from 0.82, or to improve our power factor from 0.8 to 1. Okay, so this is what we have to say. Okay, this is the rating of capacitors, or I would say 3 capacitors. This is the rating of capacitors which must be connected to improve the power factor from 0.8 to 1. Okay,